I'm Chandrasekaran. I will talk about hypergraph kcut for fixed k in deterministic polynomial time. This is based on joint work with Chandra Chekuri. A hypergraph is specified by a vertex set and a collection of hyperedges. A hyperedge is a subset of vertices. If every hyperedge has at most two vertices, then the hypergraph is simply a graph. So in this sense, a hypergraph generalized graphs. In this work, we are interested in hypergraph cuts and hypergraph k-cuts. A subset of hyperedges is said to be a cut set if its removal leads to at least two connected components. In this example, the removal of the red hyperedge does not lead to two connected components, so it does not form a cut set. But the removal of the red and black hyperedges lead to two connected components. So the red and black hyperedges together form a cut set. More generally, a subset of hyperedges is said to be a k-cut set if its removal leads to at least k connected components. In this example, the removal of the red and orange hyperedges leads to three connected components. So the red and orange hyperedges together form a three-cut set. Note that they also form a two-cut set. Equivalently, a subset of hyperedges is said to be a k-cut set if it crosses some k partition of the vertex set. A k partition of the vertex set is a partition of the vertex set into k non-empty parts. A hyperedge is said to cross a partition if it intersects at least two different parts. In this example, here is a three partition of the vertex set. The red and orange hyperedges cross this three partition, so the red and orange hyperedges form a three-cut set. In the hypergraph k-cut problem, we are given a hypergraph and a fixed constant k. Think of k as 2, 3, 4, 5, 10, and so on. It is a fixed constant that is independent of the size of the hypergraph. We would like to find a minimum cardinality subset of hyperedges whose removal leads to at least k connected components. The special case of the hypergraph k-cut problem, where the input is a graph, is known as the graph k-cut problem. Hypergraph k-cut differs from graph k-cut in a structural sense. In graph k-cut, for connected graphs, the removal of a minimum cardinality k-cut set will lead to exactly k connected components. Whereas in hypergraphs, even for connected hypergraphs, the removal of a minimum cardinality k-cut set may lead to more than k connected components. For example, the purple hyperedge here forms a minimum cardinality 2-cut set, but its removal leads to more than two connected components. So there is a fundamental structural difference between the hypergraph k-cut problem and the graph k-cut problem. The hypergraph k-cut problem can equivalently be phrased as a partitioning problem. We would like to find a k partition of the vertex set with minimum number of crossing hyperedges. In this work, we take the partitioning viewpoint as it is helpful while designing algorithms. Hypergraph partitioning problems were introduced as early as 1976 by Lawler. There are several interesting objectives while considering hypergraph partitioning. In this work, we focus on hypergraph k-cut objective, that is minimizing the number of crossing hyperedges. There are both practical as well as theoretical motivations to study the hypergraph k-cut problem. On the practical side, it has applications to clustering, network reliability, etc. The special case of graph k-cut is important for the traveling salesman problem. It is used to generate cutting planes while solving the traveling salesman problem. On the theoretical side, note that the hypergraph k-cut problem generalizes the global min-cut problem in graphs and hypergraphs. In particular, the hypergraph 2-cut problem is the global min-cut problem in hypergraphs. So it is natural to ask if we can solve this most general problem. The second important theoretical motivation to study the hypergraph kcut problem comes from its connection to the submodular k-partition problem. In the submodular k-partition problem, we are given a submodular function over a ground set and a fixed constant k. We would like to find a k-partition of the ground set to minimize the sum of the function values of the parts. The submodular k-partition problem was introduced by Zhao, Nagamuchi, and Ibaraki. It turns out that hypergraph kcut is a special case of the submodular k-partition problem. This was shown by Okamoto, Fukunaga, and Nagamuchi. In this sense, the hypergraph kcut problem acts as a bridge between the graph kcut problem and the submodular k-partition problem. The complexity of the submodular k-partition problem is open. As we will see, graph kcut is solvable in polynomial time. So the hope is that understanding hypergraph kcut will help us understand the complexity of submodular k-partition. Next, let me highlight the challenges behind solving such graph partitioning problems. For this, let's go back to graph kcut. Let's first talk about graph 2cut. The first approach to solve graph 2cut, that is global min cut in graphs, is to solve min st cut for all pairs s and t and return the cheapest. Well, one could try the same for larger constants k. For each set of k distinct terminal nodes, we try to solve this subproblem, namely find a minimum number of edges to remove so that the k terminal nodes are separated from each other and return the best. This would be a viable approach if we could solve the subproblem efficiently, but the subproblem is the multi-way cut problem, which is NP hard even for k equals 3. So the first approach that works for graph 2cut already fails for graph 3cut. So graph 3cut is already non-trivial. Nevertheless, graph kcut is solvable in polynomial time. This was shown by Goldschmidt and Hochbaum in Fox 88. They gave a deterministic n to the k squared time algorithm. Here n is the number of vertices. Recall that k is a constant. So running times of this form would be considered as polynomial time. After this, Karger and Stein gave a randomized contraction-based algorithm. As you can see, there is a difference between the deterministic and randomized runtimes. In a series of works, the deterministic runtime was improved to almost match the randomized runtime. This was the status for a long time. The last couple of years has seen exciting new techniques for graph kcut. One of the cool results from the last couple of years is showing that the Karger-Stein algorithm, the randomized contraction algorithm, in fact runs in time n to the k. This is the status for graph kcut. There has been a rich line of work, very interesting techniques for graph kcut. But ever since the first result of Goldschmidt and Hochbaum showing that graph kcut is solvable in polynomial time, the complexity of hypergraph kcut has been open. There has been some partial progress towards this question in the literature. Let me run through the partial progress to build some familiarity with the problem. The first interesting case of hypergraph kcut that one would like to solve is the hypergraph 2cut problem. This is the global min cut problem in hypergraphs. We can solve global min cut in hypergraphs if we can solve min st cut in hypergraphs. Here is one approach to solve min st cut in hypergraphs. Consider the bipartite representation of the hypergraph. Here we have nodes corresponding to vertices of the hypergraph on the left side and nodes corresponding to hyperedges of the hypergraph on the right side. And each hyperedge node is adjacent to all vertices that it contains. This is the bipartite representation of the hypergraph. In order to solve min st cut in the given hypergraph, it suffices to solve a node capacitated max ST flow in the bipartite representation, which can be done in deterministic polynomial time. So we can solve min ST cut in hypergraphs in deterministic polynomial time, which gives a folklore way to solve global min cut in hypergraphs. Do keep this fact in mind. Min ST cut in hypergraphs can be solved in deterministic polynomial time. We will come back and use this later. Besides the folklore way of solving global min cut, there are also ordering based algorithms and random contraction based algorithms to solve hypergraph 2 cut. The next interesting case is hypergraph 3 cut. Xiao gave a deterministic polynomial time algorithm to solve hypergraph 3 cut. So what remains open is the complexity of hypergraph k cut for k at least 4. The next interesting restriction that has been considered in the literature is on the input family of hypergraphs itself. The rank of a hypergraph is defined to be the size of the largest hyperedge. If the rank of the hypergraph is 2, then the hypergraph is simply a graph, and we know how to solve graph k cut. If the rank of the hypergraph is a constant, then intuitively the hypergraph behaves like a graph, and intuitively the techniques for graph k cut should port over for hypergraph k cut in constant rank hypergraphs. This was formalized by Fukunaga, who gave a deterministic polynomial time algorithm to solve hypergraph k cut in constant rank hypergraphs. So what remains open is the complexity of hypergraph k cut for k at least 4 in arbitrary rank hypergraphs. That is when the input hypergraph could have large hyperedges. A couple of years ago, we took a solid step towards answering this question. We gave the first randomized polynomial time algorithm to solve hypergraph k cut in arbitrary rank hypergraphs. Our algorithm was followed up by Fox, Panigrahi, and Zhang, who gave a faster randomized algorithm. Both our algorithms are based on random contractions, which do not extend to submodular k partition. Moreover, when we talk about the complexity of an optimization problem, we want to bring it into the complexity class P. So we would like deterministic polynomial time algorithms. That brings us to the main result of this work. We give a deterministic polynomial time algorithm to solve hypergraph k cut in arbitrary rank hypergraphs for every constant k. The main technique underlying our deterministic algorithm is to use min ST cuts to recover the parts of an optimum k partition. To tell you more about the technique, let me take a step back and recall the technique introduced by Goldschmidt and Hochbaum for graph k cut. In graph k cut, we're given a graph and a fixed constant k. We would like to find a k partition of the vertex set with minimum number of crossing edges. The approach taken by Goldschmidt and Hochbaum is to try and recover a part of an optimum k partition. If we can recover a part of an optimum k partition efficiently, then we can remove this part and recurse on the remaining graph to find a minimum k minus 1 partition. To elaborate on this approach, I will make two simplifying assumptions in the rest of the talk about the input graph. I will assume that all cut values in the input graph are distinct. This ensures that min ST cuts are unique. Secondly, I will assume that there exists a unique optimum k partition in the input graph, which I will denote as V1 through Vk. These assumptions can be relaxed with careful tie-breaking rules. I do not want to bore you with the tie-breaking rules, so we will work under these assumptions. Now, in order to recover a part of an optimum k partition in graphs, Goldschmidt and Hochbaum show a clean structural result. Here is their structural result. Let us look at the optimum K partition V1 through Vk. Without loss of generality, let V1 be the part with cheapest cut value among the parts of an optimum K partition. Goldschmidt and Hochbaum showed that for every subset T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S inside V1 of small size, of size at most k minus 2, such that the min ST cut is exactly V1 V1 bar. Next, let us see how to use this structural theorem to get a deterministic polynomial time algorithm for graph kcut. The structural theorem allows us to enumerate a polynomial-sized family of subsets containing V1. Here is how we would do this. We initialize a family to be the empty set. For each subset S of at most k minus 2 vertices and each subset T of k minus 1 vertices, we compute the minimum ST cut, UU bar, add U to the family. The structural theorem tells us that this family F will contain V1. Why? Well, consider applying the structural theorem to a set T that has exactly one vertex from each of V2 through Vk. The size of the set T is k minus 1. The structural theorem tells us that there is a subset S of size at most k minus 2 such that the minimum ST cut is V1 V1 bar. Such a pair of sets S and T is considered by the procedure, so V1 will be in the family F. Also note that the size of the family is n to the order k, and the time to compute the family is n to the order k min ST cut computations. Min ST cut computation for graph can be done in polynomial time, so the runtime of this procedure is n to the order k. With these observations, here is the algorithm for graph kcut. We first compute the family F. For each subset U in the family, we recurse on G minus U to find a min k minus 1 partition, P1 through Pk minus 1. And we compute the cost of the k partition, U comma P1 through Pk minus 1. And we return the cheapest k partition among all computed. The correctness of the algorithm follows from the fact that the family F contains V1. Let's talk about the runtime. The time taken by the algorithm to find a min k partition on an n-vertex graph is the time to compute the family plus the size of the family times the time taken by the algorithm to find a min k minus 1 partition on an n-vertex graph. Substituting the bound for the size of the family and solving the recursion shows that the runtime is n to the order k squared. This was the approach taken by Goldschmidt and Hochbaum for graph kcut. Next, let me tell you about our technique to solve hypergraph kcut in deterministic polynomial time. Our approach closely follows the approach of Goldschmidt and Hochbaum. We also try and recover a part of an optimum K partition. To elaborate on our approach, I will again make these two simplifying assumptions. All cut values in the input hypergraph are distinct. This ensures that min ST cuts are unique. And there exists a unique optimum K partition, which I will denote as V1 through Vk. In order to recover a part of an optimum K partition, we also show a structural result. Let me state the structural result and then compare it to the structural result of Goldschmidt and Hochbaum. Let us look at the optimum K partition, V1 through Vk. Let us look at an arbitrary part of the optimum K partition. Let's look at V1. We show that for every subset T that is disjoint from V1 and intersecting each of V2 through Vk, there is a subset S of small size, of size at most 2k minus 2, such that the minimum ST cut is exactly V1, V1 bar. This structural theorem differs slightly from the structural theorem of Goldschmidt and Hochbaum for graphs. In fact, this structural theorem was not known even for graphs. Let me compare this structural theorem to the structural theorem for graphs shown by Goldschmidt and Hochbaum. Firstly, the structural theorem of Goldschmidt and Hochbaum for graphs relies on V1 being the part with cheapest cut value. In contrast, our structural theorem holds for an arbitrary part V1. So it holds for each of the parts V1 through Vk. There is nothing special about V1. In this sense, our structural theorem is stronger than the structural theorem of Goldschmidt and Hochbaum. On the other hand, since our structural theorem aims to recover an arbitrary part of the optimum K partition, the bound on the size of S is larger than the bound on the size of S that appears in the structural theorem of Goldschmidt and Hochbaum. Our bound is 2k minus 2, their bound is k minus 2. But we do show that the bound of 2k minus 2 in our structural theorem is indeed tight. Secondly, the proof of the structural theorem of Goldschmidt and Hochbaum that they gave is based on the properties of the graph cut function. It is a bit hard to follow. In our work, we split the proof of our structural theorem into two parts. The first part relies only on the submodularity of the hypergraph cut function. The second part uses further properties of the hypergraph cut function. The proof of Goldschmidt and Hochbaum is a bit hard to follow. I encourage you to look at our write-up if you're interested in understanding what is going on in their proof. One final remark, Queran in '98 claimed that Goldschmidt and Hochbaum structural theorem extends to symmetric submodular K partition, but subsequently he retracted it. Using our modularized proof of our structural theorem, we can in fact show that Goldschmidt and Hochbaum structural theorem indeed holds for symmetric submodular K partition. We discuss more about this in our upcoming SODA work. In the interest of time, I won't go into the proof of our structural theorem for hypergraphs, but let me quickly show you how we get a deterministic polynomial time algorithm for hypergraph kcut using this structural theorem. Our algorithm is much simpler than the algorithm of Goldschmidt and Hochbaum. The structural theorem again allows us to recover the parts of an optimum K partition as follows. We initialize the family F to be empty for each subset of at most 2k minus 2 vertices S and each subset T of k minus 1 vertices. We compute the minimum ST cut UU bar, add U to the family. The structural theorem tells us that this family F contains V1 through Vk, all parts of the optimum K partition. The size of the family is n to the order k, and the time to compute the family is n to the order k min ST cut computations. Recall that min ST cuts in hypergraphs can be computed in polynomial time, in deterministic polynomial time. So the runtime of this procedure is deterministic polynomial time. This procedure returns a family F, which is a polynomial-sized collection containing all parts V1 through Vk of the optimum K partition. With this observation, here is a simple algorithm for hypergraph kcut. We do not have to recurse, unlike Goldschmidt and Hochbaum. We can simply consider all possible K subsets of the family F that form a K partition and return the cheapest. The correctness of the algorithm follows from the fact that the family F contains V1 through Vk, all parts of the optimum K partition. The runtime of the algorithm is the time to compute the family F plus the time to run this algorithm on using the family F, which is the size of the family choose K. Substituting the bound on the size of the family, we see that the runtime is n to the order k squared. To wrap up, our main technical contribution is showing the structural theorem that min-st cuts can be used to recover the parts of an optimum K partition. It leads to a deterministic polynomial time algorithm. The runtime of the algorithm is n to the order k squared min-st cut computations. We also show a better structural theorem, which leads to a faster algorithm. It leads to an algorithm that runs in time n to the 8k min-st cut computations. There are several interesting open questions in this area. Firstly, can we improve the deterministic runtime? The deterministic runtime that we show is n to the 8k min-st cut computations. Can we solve hypergraph kcut faster than this? It would also be interesting to improve the randomized runtime. Secondly, can we enumerate all min k cuts in hypergraphs in deterministic polynomial time? We do know how to do this in randomized polynomial time. Doing this in deterministic polynomial time might again generate some interesting structural results. And finally, going back to the motivating problem, can we resolve the complexity of submodular K partition for fixed constants K? Thank you very much for your attention.